reasonable request.
Okay, I'm starting. Let's see if it's, I'm believing it's online. We'll just forget it. All right, auditors, I hope you're comfortable. If you're on the internet. Hey, good morning. Happy Friday. What better day to do fun stuff than Friday? And that's why Bayes is Friday. That and everybody else had their courses all throughout the rest of the week. So, I've got a wonderful class prepared for you today. Ben, yes?
Yeah, just a question before jumping into the new stuff. Sometimes when I run the Gelman-Rubin,
Yes.
it tells me one of the components is not positive semi-definite.
Yes.
But if I tell it that it's not multivariate,
yes,
then it's okay.
That's what happens. And so a lot of times if there's some type of dependency somewhere in what happens, and if you're recording deviance, I think that's the part that can get there. The other part is if there's a constant somewhere in the chain,
sure,
can blow it up. I think a lot is the deviance with the model itself kind of gets this way. Then it will blow up. So you have to tell it the multivariate equals false.
And that's okay?
That's okay. Yeah, I don't know of a lot of people who look at multivariate anyway. So the other option with it is to try to pass everything but the deviance to it.
Right.
Which also tends to be a pain because you have to inspect the object and figure out where that is to pass.
Part of me just wants to be like, I ran a linear model with like 20,000, so it's probably fine.
Yeah, yeah, it's okay. Yeah, it's that's basically it. Okay. Yeah, I was actually going to ask before we jumped into these things. Anybody have any homework questions? Homework's due like tonight, so we could still chat about it. Maybe.
Is it okay to submit the derivation in a Word document?
Yeah, it's fine.
Okay.
Totally fine. Although I will tell you, if you copied and pasted the markdown that I put, you can change the equations in it. And that's sort of where I was going with it. So you're welcome to copy and paste the markdown to begin with, and start taking the parts out of the equations that make it work. That's sort of where I was going. If you've never used LaTeX before, that makes it's really messy. But the markdown just cuts it down to just be the symbols within the dollar signs, and most of that. If you would like to know more about it, just send me an email. I'm happy to. Other thoughts or questions? No thoughts, no questions. None of the above. Anybody hate it? Was it hard? It was hard? I'm sorry. Too hard? Went from like too easy for Thar and then to too hard. No, I don't. What? Okay. So, that's good to hear. I need to hear feedback. Anybody else? It's hard, right? I mean, it's not easy to get through. It was hard for me to sort of do the derivation already as well. So just putting it out there, right? So this is part of what goes on. And if you're feeling that that's hard, that's really good. That doesn't mean I'm going to fail you, right? And you notice the way I've tried to get this, right? You're trying.
Challenge accepted.
No, there's no failing this class because you try it. If it didn't work out, or if it didn't work out to what I expected it to be, which I'm giving lots of leeway, you get to try it again, right? With feedback. So it's not that I don't have this view. I actually learned this from the person over here on the right. I don't have this view of classroom learning as you've got to pass this test, and you got to, like, education is one of the most forgiving fields ever. Right? You think about how many, like, if you screw up in education, if you just have a bad semester, even in grad school, you can recover from it somehow. It may take you longer, you may have to go a little bit different rate, but there's always doors open in education. And so I'm trying to make this class that way. The other thing I want you to understand is sometimes it's going to be hard, but that's cool, right? And I did hard things in grad school, and I'm like, when am I ever going to use this? I remember being in second semester of math stat in statistics, the graduate level, to get my master's, and they were getting into admissibility of estimators and whatnot. I'm like, I'm never gonna use this stuff. It's hard. And 6 months later, for like my dissertation, I had to go and look that stuff up again, right? So you never know when that stuff's going to come up, but working with it, even if it's hard, is sort of the goal of me to try to get that to you. But in that regard, it's okay to make it feel hard. You don't have. It's not going to feel. It's going to feel. It would feel hard for me too, as a professor, let alone as a student, right?
Actually, I have an issue in plotting the trace plot for the MCM.
Yes.
There are so many because there are so many parameters.
Yes.
Distributing, they complex cluster together, so it become very small. I don't want to know how to resize the output plots.
Ah,
I can plot one by one. So
Good question. There's multiple ways to go about it. None of them are as easy because when you're using the trace plot command,
yeah.
if there's not a built-in option for it, you have to go and resize the graphic itself, and the command may resize it. So in R, let me just give you the command. This is because I worked with R. I'm old school R. I'm not like tidyverse R or whatever R. Clean R, cleaner. No. Go Google tidyverse. You'll see. Anybody else the tidyverse? Are you like? Oh, there it is, right? With ggplot. All right, well, base R is like everything else. Base R is, I speak that like I dream in base R. That's just how it works. But if you want to change the number of components to the display, the command is par, and then mf row equals C, and then it's rows and columns. So if instead of having, right now, if you have if you have a trace plot and a density side by side, they usually do 8 total, so it'd be 4, 2 is kind of the default. If you change that to like 1, 2, you'll just see 2 side by side. The other part of that is you may have to go in and trace each parameter separately, like in a loop. But I will also add that we're going to see today, probably not necessary to inspect the plot of every one of them. You can use if this is the Bayes problem, like problem 2, you could do Gelman-Rubin diagnostic if you want to as well. So, and that's part of the issue. I think when we start working in the classroom and we're getting into Bayes, the examples are, here's 5 parameters. That's a long model, right? Today, we're going to quickly have like 300, right? And that's only because the sample size is like 180, right? If our sample size was 300 or 3,000, it would be like 3,000. Can you imagine going through 3,000 plots? No, it's probably not going to work. So, hope that helps a little bit. I don't know if that exactly helps, but I hope it does a little. Other questions or thoughts, homework-wise? If homework is insurmountable, let me know. Also, your feedback helps so I can understand how to structure class better the next time. Okay? Yeah.
This is not directly related to homework, but the Jefferies prior is an improper prior.
Yes.
How much do we care about that? Like,
I don't.
Matter about?
No, see, this
This
is a great comment because improper priors are only improper on paper.
Right.
Because if you have a uniform, so let's talk about uniform prior. So what's an improper prior, everybody? Everybody want to suggest what that is? An improper prior is a prior that isn't a PDF. Right? So what do I mean by that? If you think of, let's imagine in the Jefferies prior basically said the prior density for all betas is equal to 1, right? So it's a flat line equal to 1 extending across the real number line from negative infinity to positive infinity. That flat line would map onto a uniform density. That uniform density would have bounds of infinity and negative infinity, which you'll never reach, right? So that's what makes it improper. Like if you think of the uniform density, it's 1 over, was it upper minus lower bound, right? So positive infinity minus negative infinity, good luck, right? Infinitesimally small, but equal. So here's the fun thing about the improper prior. They're improper when you write it down. In our computer, there is a bound. It's very, very large. So the way I would like to say it is effectively it's uniform over the space of floating point, double precision floating point numbers. Because now all of a sudden, as soon as you establish a bound, even if it's whatever the max number, does R have a max function? A max number function? Anyway, if those of you who program a little more hardwired languages, and I think Python does as well, you can talk about how big the numbers can be and how small they can be with respect to the architecture you have on your computer. That bound is now the upper and lower bound and now becomes proper.
So even with that though, with taking 1 as the density, that's still not a PDF.
No.
Right.
No.
But I guess it doesn't matter because we're dealing with things that are proportional.
Yeah, and it's effectively proportional
when it comes to when you worry about. So improper priors often are not really panic stricken. The bigger thing that people talk about, again, there's several things with priors. Improper priors tend to not want to have this. Well, Jefferies prior is an improper prior, but it's okay because it looks like ML, right?
Sure.
The other one that people talk about is the Jefferies prior sort of came out as a way to circumvent the other big problem, which was is the posterior resilient to parameter change, right? To transformation. So is the posterior distribution invariant to transformations of parameter? And under the Jefferies prior, it is. So which one do you want to? And I think the reality of it is we're talking about such small. We're talking about the beauty of math, right? But when it comes to the actual practice, I think it's most of the time these are infinitesimally small that it's not going to affect us a whole lot. But that's most of the time. There may be some special cases, and then I think there's some papers by Gelman in the early 2000s actually talk about the variance component prior that talk about when those might be and how that might cause issues. So that it's something to think about, but it's not something to like and stop everything with.
One more.
Yeah, please. It's great.
Question.
Uh-oh.
So it's not that bad. So in our derivations, like you were doing in class for, the conjugate prior, giving you your posterior. People will say the posterior is distributed as multivariate normal with this mean vector, but it's not, right? It's proportional.
That's
to,
right.
To that. But,
that's right. That's proportionality is fine.
Is it bad if they say distributed as?
No.
That's technically not the case.
Well, so technically, I believe you can show it is. It's just you may not be able to specify what the normalizing constant is.
Right.
Right. So if you carried those constants that didn't involve the parameters through, you'd have a big pile of them. They wouldn't look really nice.
Right.
You could probably make them look really nice. I actually think you would really be able to do that. I don't think I could. But the idea of it is, with the core of the distribution the same, you can say this is proportional up to that normalizing constant. Right. And if you go there, if you can see that, then you could effectively figure out what that normalizing constant happens to be in some cases. Like the multivariate normal, you can quickly show it. Not quickly. It's not easy, but you can make that happen.
So yeah, it's multivariate normal, but not with the normal normalizing constant.
That's right. It'll be another normalizing constant. And technically, if you go in with the prior, if you're looking at the joint posterior of beta and sigma squared, then it's sort of this multivariate normal slash inverse gamma, right? So it's not actually multivariate normal. It's multivariate normal times the inverse gamma, and that's where that normalizing constant really gets messed up.
Sure.
But I think it's sufficient just to say you don't need to find that.
Cool.
Because if in the Gibbs sampler, you need to have it because you need to draw from the proper distribution. But in a lot of samplers, it actually cancels. So I hope that helps.
Yeah, for sure.
Other questions or thoughts? We were rushing through Metropolis at the end of last time, and I had this ratio that I wrote down, right? And in that ratio, a lot of those constants start to drop out. Because when you take a ratio of the prior and proposed and otherwise, you start to see a canceling happening. Or across the chain it will as well. They're sort of the one thing that, if you think of Bayes' theorem has posterior times prior divided by marginal, right? And marginal is usually really hard to compute. You have to integrate across things. So certainly the marginal goes away. But if you think of marginal as a way of thinking about, it's sort of a version of a normalizing constant. That's where I'm going to. It's not always that's the case. I'm thinking of all the exceptions as I'm talking here, and I'm quickly running out of words to say. Pinning myself into a box. Okay, what do you remember from last time?
Acceptance.
Accept. Reject. Would you have preferred me to swap out that derivation problem for a coding problem? No. Because I was thinking about doing one or the other. Because both of those are things that I end up doing in life that I never really did in class. Does that make sense? And so I'm trying to give you the life experience skills in class now. You may not, your life will go in a different direction than mine. I know that, but who knows what, having more skills is never a bad thing, I feel like, right? Or at least knowing where to start. Okay, this week I did things a little bit differently with respect to class. I actually, the horror, created slides. Oh no, I have slides. I'm sorry, I went away from my thoughts. So here's the deal. I have like 2 grants due in like 3 weeks. I have a class to prep, you know, blah, blah, blah. We all have deadlines. But I have a bunch of other stuff that either I made or someone else I know who's really good at teaching made to draw from. So realistically, why don't I just draw from that, right? But we're going to get into psychometrics today, even with its slides. What do you think about that? It's finally psychometric time. Now, here's the other thing about this class that's a little bit weird, is that like there's not enough Bayes to be super familiar with Bayes for any one type of analysis. So everything okay? Hope you're that's good. So for any one type of analysis, you may be like, well, I wish I knew more about Metropolis, or I wish I knew more about coding. But my thought is we're going to repeat all those things we just saw before. We're now repeating today. Maybe not the derivation as much. If you'd like to, you can certainly do that. But we're gonna keep repeating that in every analysis. So what you just saw before, when we sort of went through, even though it probably felt insufficient, it still took a number of class periods to do so. We're going to repeat. We're going to repeat. How do we set up the code? What's the model? What's the prior? What are good choices for prior? What happens when we're done analyzing that? And now we're just going to change the model every week. Cool? We'll see how this goes. The thing about, so let me see here. I learned CFA. I love me some CFA. This has always been a favorite topic of mine because it was like the first class I took in grad school. But one of the questions I have for you is, why do we use it? This relates to our class actually. But why do we use CFA? Particularly in measurement, in educational measurement, psychological measurement.
Because you have a model in mind that you think will explain some sort of behavior, and you want to see if that model fits well.
Very good, but we have other models. Why will we pick CFA for data? What I'm building toward is, how many of the data sets that you work with in up to this point in history of ed measurement, of all the examples you see in books, the typical CFA example is grab a Likert type data set, do an analysis, say, ta-da, have the horns play in your head, you know, right? How many of those data sets actually fit the assumptions of CFA? What are the assumptions, actually? We have to get into that. I'm going to say right now, the premise I'm leading up to is, there's very few data sets that would ever want to use CFA for, ever, especially now that IRT exists, right? The hard part, though, in practice, is because CFA makes the math work much easier, because effectively it's a conjugate prior. It's a linear model like we just did, and it works almost all the time, right? It's a heck of a lot easier to do CFA than it is to do IRT. Even though we learn IRT and we love it, the model fit industry is different in IRT. It's very hard to do. The model estimation industry, particularly if you've got more than 1 or 2, 3 factors, very hard to do. But the big thing that we have to worry about in CFA is the primary assumption, which is effectively we get the assumption on the outcome like we do in regression. Actually, it's a little bit stronger than that in regression. We're going to assume our data, each observation, each item's score is normal, right? So normal means continuous, right? How many of your data sets featured continuous data to use CFA for? I'm going to go out, I'm in grad school, I may have seen 1, right? So I'll tell you where I think CFA comes in handy. It helps us establish certain things that are easier because of math. It helps us understand the connection to other methods. I don't want to compare, yeah, and it goes from there. I may compare CFA and EFA in just a little bit. But the idea is effectively, how do we go and what happens to our data, our analysis, when we use these categorical scores and we pretend they're continuous and normally distributed? Well, you typically hear, how many categories do you need? Have you heard that before? Have you been told that before? I want to hear it. If you've got Likert-like data, and this is, you have a 3-point scale, can you do a three option? Agree, not sure, or disagree. Can you do CFA on it?
I've seen it done.
You've seen it done? Mm-hmm. How about 2 options? Yes, no. Oh, screw that. That's out. Can't do that. That's like, you're going to get locked up in psychometric jail for that, right? Am I right? But 3, you've seen it done. 4,
Seen it done.
seen it done. Feeling better. 5, oh wait, isn't there an article?
There's several.
Okay, but look at that. Look what you're reduced to. I don't know. Maybe. I guess. Sort of. It depends. Let's find out, right? No, it's a bad idea, right? So I'm going to just put it out there. CFA is a bad idea in almost all data. The only reason we use it is it's way easier than using IRT. That's where enter Bayes though. So when you're doing Bayes for CFA, if you're like me putting together this week's example file, which is an R, you're like, why the heck are we doing it for this? We're not, although I'm going to make a twist on it to show where we could. We're using this to set up IRT, because now you can properly analyze the data, and all the steps that might blow up before, we can start to resolve with priors. Right? Those cover a lot of estimation ills. And not only that, the issues with multidimensionality and how hard it is to get a thing to converge, we can also start to remedy as well. Start to. So, thoughts, questions? Face is too far away. All right, cool. Well, let's jump in. This is your CFA model. Thank you, Lisa, for your slides. I believe we sort of passed some of this back and forth.
You can tell which parts are fine, I think.
Yeah.
I like colors.
Yeah. Hey, I got purple on today. I'm wearing green. I've got color. So CFA, we've got the unit of analysis is typically an item. This is an item response for this Y is the response for item I subject S equal to some type of item mean or item intercept. Factor loading times a factor for a single factor model plus error. Okay? The factor is for the subject S. This looks like linear regression. Just you didn't collect X. Oh, what do you do then? Shoot. But here we go. The intercept in linear regression is the expected value of the item when the predictor is equal to 0. Right? So in this case, the item intercept is the mean. We have to start to make certain types of identification, model identification, scale identification issues. There's sort of layers of identification in CFA. One is scale identification. You have to figure out the mean and the variance somehow. And there's multiple ways of doing that. So often the mean is set to 0 of the factor, particularly when you're looking to touch data for the first time. You're not doing some type of growth model or growth of factors or something along those lines. So that means the item intercept actually becomes the mean of the item if the mean of the factor is equal to 0. The slope of the factor is our factor loading. So we interpret it the same way. For every 1 unit increase in the factor, the slope goes, the expected response goes up by lambda, the factor loading. Right? Now, what is a 1 unit increase in the factor? That depends on how you identify the factor, because more commonly, we end up doing an identification method that allows us to estimate the variance of the factor itself. So let me ask, how many of you, when you did, if you've learned CFA before, how many of you learned it with where you standardize the factor, where you set the mean to 0, set the variance to 1? And then, is that the primary way you analyze data? Cool. Have you done the marker item version before? Where you set one item as loading, usually to the value of 1, and you estimate the factor variance? Done that way too? Okay. They're equivalent models, right? The same thing goes with the mean itself. Often we set 0 for the mean, but if we fix one of the items' intercepts to 0, we can go and estimate the mean itself of the factor. The mean of the factor really comes from the data itself. So it looks like this. Any questions about CFA, this model? Does this start to bring back the good times? We all love CFA. And then there's pictures. Lisa's picture. You've got, which I always say, the first thing, you know what I'm going to say next, right? What do I say when I put this up?
It's not a model.
It's not isomorphic with the mathematics. Because circle plus square does not equal triangle.
I had to put this in a triangle, and so it was. I hate triangles.
Strong stance to take.
I'm looking for the octagon, really. Save that for like the higher order factor. Oh, that's right, the rectangle. Yeah. Can we go with a rhombus, maybe? I almost get a sense that, so this is a nice schematic diagram, very much like the network graphs we saw before. Here we've got the factors are circles. The things you can't observe are circles. You've got arrows implying that the relation, the value, just like the network graphs that we saw in kind of the first couple weeks of class with the book, when we talked about the graphical models. Really what we're saying here is the distribution of y is conditional on f and actually e itself, right? So it's just, sometimes you said, in most of the places that we saw the graphical models in the book, we wouldn't see these e's more often than not. The parameters themselves in the graphical model would enter in another way, right? In some of the like the bugs networks. But this is just another, now that you've seen this, for me, I grew up with this first, although not the triangle. Who has a need for that? It's trying to express quickly in words what's happening with a very complicated mathematical form. But it's never going to be sufficient for all math. Like math is the thing that works the best, and then after this it works. So it's very good for audiences where you're trying to get the point through, but if you're going to just put this in a paper somewhere you got to go describe the model itself. Otherwise, forget about anyone trying to retrace your steps. So there's different types of solutions themselves. What do I mean by solutions? You get data out of the computer itself. You get numbers. One is just the raw numbers that come out. These are called unstandardized. Right? So you get a lambda there. You can describe what the variance of y happens to be. Another is a standardized solution where you can say, oh wait, what if I estimated the factor variance, what would my numbers be if I changed my factor variance to 1? Or I changed both my factor variance and my variance of y total to 1, right? Those are standardized. The standardized helps provide a sort of a common metric itself that goes through. You've got model equations themselves. Basically what we're doing is a multivariate regression analysis. The items that purport to measure a factor, load onto a factor. I like to say the word measure, that's my way of putting it. Effectively have the loadings estimated, and otherwise they have 0 for the loadings. And this is the part where I'm going to say, why am I doing CFA? How many of you like EFA? Or better yet, how many of you want to do EFA before you do CFA?
Sorry, I just threw up in my mouth.
I'm not trying. Lisa doesn't want to do EFA. I like to say friends don't let friends do EFA.
Yeah. I do though.
You do?
You said like the first day of class something about it, and I'm like, oh. Well, what do I not know?
So when you learn EFA, how do you learn it? And this is going to become really relevant really quickly. Let's think of it this way. Back up. Keep that question in your mind. What is EFA, first of all? And how do you express that as a model equation? Because what's going to happen when we code our model, the first step, we go and write down, okay, what do we need to code this? We need the likelihood of the data given the model, right? Of the parameters. What's that for EFA? It depends on which version you're using. Anybody want to offer? What's that for CFA? I'll tell you, just right now. It's multivariate normal, right? Because what ends up happening here, we saw for one y across all the subjects before, the likelihood of the data was multivariate normal, right? We had, but with a very certain covariance structure. Here for CFA, we have more data, same number of people. So our likelihood is still going to be multivariate normal. The likelihood conditional on the factor itself is multivariate normal. The mean vector is given by the vector of item intercepts if we identify, in the way that we are identifying our factor, let's say standardized to begin with. The factor variance represents the error variance, the covariance matrix of all of our errors represents the error in that term, right? So we can express that right there. We can go a step further, and the part you may have learned also, so here, let me just start writing. Maybe I can start writing. Uh-oh, if I've been, I don't know if I did something wrong. The stream may not be good now. So me and my stream. All right, anyway, the issue that we're gonna see pretty quickly, if I start writing this down, maybe, think about it. Yeah, maybe not. Okay, well, I won't write it down. Oh, there it goes. Hey, iTunes, go away. There it is. Okay. Let me just get some type of written picture here. So now what we have for each person, and I can't draw. Okay, forget it. I'll draw it on the board, and people online won't see it. But that's okay. Each person, we say the distribution of y, the vector, for a person, given f. We may have a vector here, right, for a person. And I'll just put dots there, because in days we typically have other things that's conditional on all the random terms, right? This thing is effectively MVN, right? So the mean vector is mu. All those item intercepts are, all those item intercepts over there are going to the mean vector, right? And the variance covariance matrix is actually given by, so we go a step further, we say that the vector of ease for each person is multivariate normal. It typically has a mean vector and a covariance matrix given by psi, right? You've seen that before, sort of?
That's coming.
It's coming, I know, I'm just trying to jump the gun here. So conditional on the factor, not the marginal distribution of the data, but conditional on the factor, that turns out to be the variance covariance matrix. Right? But more often what you see is the marginal of the data, which is f of y itself, right? When you put these together in your typical setup, you typically say, oh, my f is also multivariate normal, right? And let's just make this a little bit simple. We'll call it a mean, we'll standardize, sort of standardize it. We'll have a mean vector of 0, And then we have a factor covariance matrix that often gets denoted with as a phi, right? So when you look at this, you can think of this is, now if we put this into Bayes terms, distribution of data is this thing in the middle. This is one of the priors that we have, right? So if we want to marginalize, if we want to just look at the distribution of y, this is the typical form that you end up seeing with factor analysis. This is multivariate normal, where the mean vector is still given by mu when we have a factor mean of 0 for the vector. But now the variance covariance matrix is a very familiar form, which is lambda, actually, capital lambda, the lambda transpose plus psi, right? You see this equation before in your life? Yeah. Okay, so what this is saying is the distribution of our data, y, is this right here. Okay, now getting back to my question. Now, if I were to go and think about where my model goes in days, what we're going to quickly see is this thing right up here is the model we're going to use for the data because it's conditional on the factor. So we can express that. But going to the EFA sidebar that I want to get into, as to why I'm doing CFA, not EFA first, does EFA have a similar form to this? How many of you learned EFA using maximum likelihood? Or do you do some type of principal components or eigen decomposition version of it? So the principal components eigen decomposition is sort of using the black and white TV, right? So it's like the tool that came out first. It takes your covariance matrix or your correlation matrix, does something, depending on which version of it is, does something to the diagonal of it, and then does some type of spectral decomposition to go and get eigenvalues and eigenvectors, and you interpret those, right? Or rotate those, right? But here in ML, though, if you go to ML, actually, let me back up. If you take the straight PCA, if you take a covariance matrix, go and decompose it into eigenvalues and eigenvectors, you have one eigenvalue for every variable that's in your data. You have to determine how many factors you have. Usually you say, where's the elbow? How many eigenvalues are bigger than 1? Blah, 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 right? You know what I'm talking about? Right? There you go. In ML factor analysis, with EFA, you don't get, so technically, let me back up before we get ML. Again, with that EFA with principal components, having an eigenvalue for every variable effectively says, if you really wanted to, you could have as many factors as there are items. It'd be a really bad idea. Why would you do EFA? Right? But you could do that, right? In ML, that is not the case. You can't have that. Have you learned that? Because in ML, you have this pesky thing called degrees of freedom that talk about identifiability. But let's get into the likelihood function first, right? In ML, turns out the likelihood function is identical to EFA. EFA and CFA and ML are identical likelihoods. Identical, right? So if you're not doing ML, you're shooting yourself in the foot for a couple reasons. Number one, if you have any missing data, your missing data protection is less. Right? You have to assume missing completely at random. It's bad. Number two, really unstable method. So let's flip to ML. In ML, the model now effectively will have, instead of zeros here, a bunch of lambdas. Right? Okay. How is that possible? It's not identified, right? ML, factor ML, EFA, has to come up with a set of constraints that are minimal to allow global identification from a statistical sense. Because you can't estimate every factor loading. Have you ever heard of these? What are they? Here's the question I asked, because you have to dig to actually understand this. The principal components machine that started got us all looking to see where all the factors and eigenvalues and stuff were. But under ML, they don't exist. They're not there, right? It's a different scenario altogether. So, most commonly, where you see this is we have to make a set of constraints they're based on the number of factors we have. For instance, for 2 factors, we have to set 1 factor loading equal to a value. We cannot estimate it. If we allow the factor covariance matrix to be an identity, or correlation matrix to be identity, right? So if you want to get a correlation between factors, you can't do that. Well, the set of constraints that typically get enacted in computers is something that you'll sometimes see cited. There's a book that's a famous one. I mentioned it to you the other day. Lawley and Maxwell, which is a 1971 factor analysis book, that says basically to identify the model, one of the constraints that they came up with was to say that the matrix of loadings, right, times the matrix of error item of unique variances, effectively, times the matrix of loadings transposed is equal to some matrix delta, such that delta is diagonal. What? What's that mean? Have you seen that before?
Yeah, it tells you that psi is diagonalizable.
Possibly, but think about what it means in constraints, right? Effectively, if you work this out with 2 factors, you're effectively saying the first loading times the unique variance for the item times the second loading for the item. If you add that to doing that for every one of the items, all those have to be equal to 0, right? So, why I say EFA is ridiculous is 1, you're doing things that are not even likelihood based, and you get into trouble there. But number 2, EFA is CFA. That's a constraint. That's confirmatory right there. And what happens in CFA if you put the wrong constraints in? Well, in the paradigm of EFA, the only recourse you have is to extract another factor. Oh, this doesn't quite work. Let me go get another one, right? The likelihood ratio test would be bigger and so forth. So, if the likelihood is the same, and we have to put the same number of constraints in to minimally identify the model, what we're arguing about in CFA versus EFA is not the approach, it's about what constraints are more reasonable. How's that?
So then that's just identified?
This is just identified, right here. When this is true, this is just identified. Right? Have you seen this?
Yes, but question for you, because in EFA, people usually use it like the play tool, yes, and then use the confirmatory. You will be using, if you are speaking EFA and you are doing CFA, you will be checking the modification indices, those type of.
Yeah, it's exploratory. But what I'm trying to tell you, what I'm trying to weaken your faith in, is the black box of EFA has a constraint that's confirmatory and nobody can interpret.
Sure, I just wanted to be sure that you were not arguing that we shouldn't explore the data.
I think what you should do is do one model. If it doesn't fit, quit.
Boo!
Go to lunch.
Boo!
Plan another study. Sample some new data. Run one model and quit.
Have you ever been possessed by Crash?
No, I'm trying to think of like in theory, right? If you run an experiment, basically the confirmatory pattern of constraints is effectively it's a hypothesis, right? About how your data behave. If you reject your hypothesis, okay, I'm done. What do I do next? You quit? Or do you?
Yeah, I think the distinction you two are making is about an exploratory modeling as opposed to an exploratory factor.
And what I'm trying to say is there is no exploratory modeling. Because EFA is CFA with constraints.
No, but the way he's saying you use it, you try it, it doesn't work, you try something else, you try something else, that's exploratory.
That is exploratory. I completely agree.
Even if you're doing
I completely agree. The names of it are terrible, and if I were to call it anything, I'd call this exploratory analysis through CFA.
Yeah.
Right?
That is the whole point that I was trying to
yes,
share.
I agree with you. 100%. I was making a side tangent, and I was making an example. Because really, we should be saying, well, we failed to, we didn't, we rejected our null hypothesis. We can't do it. What do we do now? No, I'm just kidding. The idea is, to me, this is what's going on behind the scene, right? the question becomes, which constraints do you like better, that one or that one? Anybody like this one better? You like this one better?
I'll give you a non-math reason why EFA is stupid. It's not your computer's job to tell you what you're measuring.
Fair enough.
It's your job. If you don't have a clue, game over.
Yeah, I would
Game over.
in putting together this lecture, I had an interesting feeling pop in my head, and I almost reached for the EFA button. I kid you not. I kid you not. Right? Because I took data for an example. And I resampled from a test that had 10 items and 180 some odd people, 188 people, right? So I did a resample so the data weren't like the original ones, and this is not making any commentary about the test or anything else. And I'm like, does this, well, it doesn't really fit the one-factor model, but I looked at the items and sort of conjectured a two-factor model, and that didn't quite either. And I'm like, okay, well, what if, no. No, but this is probably why, so I had this interesting part where I'm like, I'm putting myself in the shoes of the people, I know I used to be one that learned, hey, EFA first, right? Why? Because when you're building an example and you have nothing to do with the data, where do you go, right? So if you really want to know where I would go with EFA, is this: a just identified model. You load up as many factor loadings as possible. You don't have to rotate. You get your result. When I grew up in class in grad school, Rod McDonald used to call this the row echelon form, which basically is a type of a flag. I don't understand, but if you look at your pattern matrix of which items load onto which factors, you put a 0, and if you have 2 factors, you put 1 0 like at the first item. Basically, this first item doesn't load on the second factor. There, you have said this is the rotation. Estimate that. If you really want to get greedy and you want a factor correlation, make 2 zeros, right? So if you really want to do it, that's the way I'd say to do it. But the reason why is because you have to make constraints to do this to work in ML. I think it's much better to make constraints that are understandable.
And there's a middle ground too between only barely enough constraints to make it work and this.
Right.
Like you could say, if this factor is really measuring X, then these 3 items can't possibly load on it.
Yeah.
And you could set those 3 to 0. Like you can have intermediate solutions between fully identified or fully, saturated versus like simple structure.
Yeah. What do you think? Have you heard this before? EFA is bad? Good. Preaching to the choir then? Anyway, I don't know. I always say that when I go to a new university and they look at me like I'm a heretic, like I'm a lunatic. You can't do that to EFA. I just did. I did.
I have to say, I've never seen anybody read EFA with so much clarity in class.
Really? That's good to hear.
Off the top of your head, no less.
No. I've
Damn.
had to talk about. So when you're one of these people who are like thought of it, I'm no longer young, but I've been young. I've been always new to universities and whatnot, and you know that there's sort of this clash of culture, right? You come in, you respect the people who've been there a lot, but a lot of the people who are there, well, this is how we teach this. I'm like, well, here, have you seen this? I have to I've practiced this by having to write this on boards of many colleagues in the past, and that they don't know what to say at that when I get there. I'm like, okay, this is my rationale for why I believe this way. So there is really no EFA, and actually there's really no CFA with the way we use it, right? There's likelihoods and constraints. And if you're not doing likelihoods, well, there's good uses for principal components, just not the way that we're trying to interpret it. Like if you have 250 if you have a survey analysis and you've collected 250 demographic variables that you need to weight by, sorry, Lisa, weight by, right? An easy way to weight by, instead of weighting by 250, is to use a PCA and take a few of the actual components and weight by that. It goes a little quicker. But.
Like you have 128 electrodes.
Right. Yeah. You're not ascribing meaning to each of the components. You're just basically using them as a part of taking data and smushing it in there and saying, I'm going to just use this instead. So anyway, blah blah blah. Okay. matrices.
Told you it was coming.
There you have it. There's the marginal model, right there. You can see the factors there. Probably all seen all that before.
Can I say something real quick?
Please.
My class. Next, previous slide. Okay. G is sigma. Thing in the middle of the lambdas, that's G. Thing on the end is R.
Yeah, if you're doing a multi-level model.
Okay.
Seriously.
C is lambda. Okay.
Yeah, this is the pattern.
See, they're smiling.
Yeah, and that's the cool thing about like this, and that's actually one direction I thought about taking it today, is with like a few changes of code, we're not doing a CFA anymore, we're now doing a random slopes model. Random intercept, random slope. Like it's just like that. So
Random elements are written variables.
they are. So it's such a close combination between the two. And if you learn one really well, like in the world I grew up in, we learned latent variables really well. It doesn't map entirely onto the random effects. There's some things, mainly design considerations, I'd almost say, you think about. But it's still there. I mean, when I was at Georgia, I had colleagues in the stat department who were really, like me, boisterous and assertive and willing to tell me what they thought. And they're like, I don't believe CFA. I don't believe in factor analysis, one of them told me. He was a mixed model guy. Okay, well, let's just, so I try to explain, once I put it as like, well, let me rephrase it as a mixed model. Oh, okay, well, why would you ever want to go and why are you trying to make inference about the error? They think of the factor as error, right? It's a very specific type of error. Am I right, more or less? I haven't taught multi-level in a while, right? Right, so, they're like, well, how would you, there would be a lot of variation in that error then, right? It's like, exactly. So we create designs, we call them tests, that have lots of items. Oh, I was like, so yes, it's quick to think about how, like a lot of the terminology is similar, a little bit of the methods is similar. It's in a different direction with a different type of research design. And I think that really expresses like the bigger part to it more than differences in model. So, other thoughts, questions? All right. So yeah, spread the word. Tell everybody I don't like EFA. Don't do EFA around Templin. He'll just, no, I'm just kidding. I really shouldn't say that because remember, Templin says there is no E or C. They're all the same. It's how you choose to put your constraints in. That's right. You want any soccer highlights? It was a great game, great match last night. All right. Okay. So let's do this. Let's go grab some code and play with JAG, shall we? Get into an example. So this time, instead of doing the R Markdown, I was getting tired of R Markdown because I didn't like having it go off of the screen. So I just built a flat R file, not even an R notebook. Old-fashioned R, okay? I'm learning that this is maybe not the best teaching tool. It's pretty good for writing. It's not there, but this is the R file that's what we see in the repository. We're going to load some packages, and let me just give you an example. Let me just give you the data story today. I want us to get into the data. I was looking for an example that will carry with us because I just mentioned before, why do you do CFA? This is a Likert test. There are 5 items, 5-point Likert scale for every item. It's going from strongly agree, disagree, neither agree nor disagree, agree, or strongly agree, right? And we're going to bring this back for IRT, and we're going to quickly show IRT with it. But here's the data. It's a bootstrap resample. So I took the original data set, grabbed a resample of 177 undergraduates at a large state university in the Midwest. The survey was a measure of 10 questions about their beliefs in various conspiracy theories that were being passed around the internet in the early 2010s. How I stumbled onto this is I was teaching a workshop for Lisa, actually, while she was building a human in 2015. And
I was after I built him, I was feeding him.
Oh, you were feeding the human.
Yeah.
Our son was born, and I taught a workshop for her at Boulder, Colorado, University of Colorado, Boulder. and flying into, anyone ever flown into the Denver airport?
Yeah.
So the Denver airport is way outside of Denver, first of all, right? And it's nuts. Like, and if you look up, like Google right now, Denver airport conspiracy, right? There's a whole list of conspiracy theories about how the thing got built. And I'm sort of making this a joke in class, and one of the students is like, well, I have these data that are about conspiracies. Yes, let's do this. This was before like fake news and all this other stuff that's come out, like misinformation and so forth. But I added gender to the survey as well, though I didn't get to analyze it. But here are the questions. You would like to see them? Number 1, the U.S. invasion of Iraq was not a part of a campaign to fight terrorism, but was driven by oil companies and Jews in the U.S. and Israel. Kid you not, that's a question.
That's a terrible question.
Isn't it?
Really.
Yes.
Not just because it's offensive in 17 ways, but it's like there's 3 different things you have to agree to in order to pick one answer for your level of agreement.
I agree. I agree. Agree completely. Certain U.S. government officials planned the attacks of September 11th because they wanted the United States to go to war in the Middle East, right? These are pretty terrible thoughts. But circa 2010, there were large factions of people who were really believing it. Actually, ever since, well, probably most of our lifetimes, it's just, you know, bigger lately. President Barack Obama was not really born in the United States and does not have an authentic Hawaiian birth certificate. The current financial crisis was secretly orchestrated by a small group of Wall Street bankers to extend the power of the Federal Reserve and further control the world's economy. Vapor trails left by aircraft are actually chemical agents deliberately sprayed in the clandestine program directed by government officials. We call those chemtrails. One time back when Facebook was easier to log into, my sister left her phone open and I started posting about chemtrails. And then some of her friends chimed in and said, it's true. So, but do you get the sense, I mean, have you heard of these rumors, these conspiracies?
Exactly one of these is true. Which one?
Not going there. This is a psychometric instrument that's sort of on the edge where this might cause a little bit of uncomfortableness coming through the questions, right? But billionaire George Soros is behind a plot to destabilize the American government, take control of the media, and put the world under his control. The U.S. government is mandating the switch to compact fluorescent light bulbs because such lights make people more obedient and easier to control.
That's true.
Oh. Didn't work on me. Government officials are covertly building a 12-lane NAFTA superhighway that runs from Mexico to Canada through America's heartland. Didn't that go by here? I don't know. Never mind. I thought it was like I-35. It does, right? I mean, it goes from Mexico to. Oh wait, does it go north of Minneapolis? I-35. It goes all the way to. I don't know. Anyway, never mind. Government officials purposefully developed and spread drugs like crack cocaine and diseases like AIDS in order to destroy the African American community. And God sent Hurricane Katrina to publish America for its sins. I kid you not, those are questions kids had to answer. If I was reading those questions, I would probably be mockingly answering on the agree, you know, whatever.
I really hope that these items aren't normally distributed.
Let's take a look. I plotted each of them. So I made this whole spiel about CFA because we assumed this about the data with CFA. It's multivariate normal. I didn't prove it, but I'm just telling you it. So, but we do know from multivariate normal that if y is multivariate normal, the vector y, then any individual y is univariate normal, right? So that means that each of these items should be normally distributed to use CFA. Let's take a look. Show us the data. This is the first question. Normal? Nah. The second question. Is this restoring your faith in people responding accurately?
Wow.
That's bimodal. By the way, I'm using these data for the latent class analysis coming up too.
That's the Berkeley one.
Yeah.
And what was the scale? Is 1 agree or is 5 agree?
5 is agree, strongly agree. 1 is strongly disagree.
Good to know.
Yep. There we go. There we go.
This is proof why any rules about number of response options can't possibly hold, because it depends on the distribution used within the response options. They could make this a 9-point scale, and hopefully it's still going to be skewed to the left.
That's exactly right. I had a, I'm going to tell this story again. Have I told you my gambling with grant money story?
No.
Can I tell you that?
Yes.
Okay, so I was part of a lab in grad school. We were studying gambling behavior. It was the professor's, like, it was his last grant before he decided to retire, and we all kind of thought it was him trying to get money to go gamble, right? He loved gambling. So he gets money, and part of the grant we had to create a survey, because there's a pathological gambling is written in the DSM. There's 10 different criteria, of which 5 or more need to be met, but some of them are pretty mild. Most of them are like, yes, I've stolen money to finance my gambling. I've lied to my friends. I think about preoccupied with gambling. Think about it often. Anyway, measures of gambling that are out there, quick screener measures, typically have most people who say no to almost everything. There's very little variability. So those in the lab believed, hey, why don't we just make it instead of 2 options, yes or no, because many of the screeners are yes/no questions. Like if you call up the Gamblers Anonymous number, they give you one of these. Well, we need more variability to sort of figure out stuff. Well, let's just put more options in, right? So we handed that out, and sure enough, we got this too, right? No is a no. Strongly disagree is a strongly disagree, regardless of whether you ask it yes, no, or maybe. Like, are you sure? No. Do you gamble? No. Do you think about gambling? No. Anyway, so yeah, that's it. So the bottom line of the story is to collect the data. We were given access to a casino boat in Peoria, Illinois. They let us set up shop with computers to do like a simulated gambling environment off the boat in the offices that they had. But we were and they let us go on the boat and try to get their patrons to come off the boat, go up to the office, do this. The incentive was we could pay you up to like $300 to go up here, so you can gamble more, right? So the casino was good with all that, right? But the way that we had to collect people is we sat around a roulette table, and we had the security camera on, and one of us was literally gambling with grant money, looking like we were part of but secretly keeping track of who's been there how long, because we wanted them to gamble for like 45 minutes or so. I can't remember exactly the number. And then once a person would leave the table, there would be some signal given by that, and there'd be someone standing over the shoulder or in the back who would go and talk to the person. Hey, excuse me, would you like to, get another up to $300 to come back to gamble with? So we gambled with all of us took a turn gambling with grant money. And finally, the other backstory of that story is that the grant itself was not like what you think about with an NIH or an NSF or IES grant.
Yeah.
This is a grant paid for by a consortium of casino operators who were concerned with people having problems gambling.
No conflict of
No.
And
No.
Where did you present a poster about this?
Las
research?
Vegas. Twice. Twice. Some of the best conferences too. It was awesome. It's like, oh wait, do we need to get to that session? Yeah, but hold on, I'm hot. This slot is hot. Elvis was working overtime for me. Anyway.
I'm in the wrong business.
Oh, those were the days. Didn't have any money, but in Vegas, if you did it right then, like the quarter blackjack machine, they had the quarter like video poker, but if you play blackjack, the odds of winning any hand on those rules about 49%. So you're going to slowly burn through your money. You play at a quarter at a time, and it was during the midweek off season, and they're all at like a bar, and so you're quarter at a time, and they would just keep filling up your drink because so it's like I get tip $1 or $2 a drink, but never mind. Things I learned in grad school, and that EFA sucks. Sorry. I gambled with grant money, and EFA sucks. God, I really sound terrible today. So, are these data something that you'd want to use confirmatory factor analysis for? No. Are these data ones that people would probably use CFA for?
Absolutely.
Yeah. So we're going to do CFA with these data.
I think the other reason that because they're taught that that's how you do SEM. If I were wanted to predict differences in craziness or whatever this trait is, then I need to do that in the context of an SEM. Well, doesn't that have to have CFA in it?
Right, yeah, and so when you sort of realize when you can put the model together like this, well, F is just another variable. We not observed it, but if we have another variable, it doesn't matter how we got F. We need a measurement model to identify F, and then we can put that in a bigger. An SEM is a bigger type of graphical model.
Yeah, I'm just saying that the idea that you can put an SEM on top of an IRT is not something that is well established in a lot of other fields.
Fair enough. All right, I'm going to stop here. We got 10 minutes for break. Enjoy. Try to wipe those conspiracies out of your mind. We're analyzing the data without respect to the veracity of truth for those.
So should we start to do